This is a clock, but it's not an ordinary clock. This one tells the time in Morse code. It shows the time of day in hours, minutes and seconds. And the seconds creeps up in a normal Morse code numbered sequence on the left-hand side of the screen. And it does it entirely with LEDs. It's battery backed. It can be selected between 12 and 24 hour time, and you can hang it on the wall. But it's not for everyone perhaps. It's great for the shack, and with this running, you'd never be late for a sked again. We could have built a clock which actually has an oscillator and beeps out Morse code as an audible tone. However, there's some people who may not like that in the household, so this is a silent clock. It just uses the LEDs. What we're going to do here is show how it's put together and assemble one from one end to the other and provide a little bit of insight into how it works. So here we go. Although it may not look it, this clock is fabricated from circuit board material. I'll just turn it around. On the back we have a plate where there are buttons for adjusting the time of the day, advance, and an LED test button, and there's a little hole here for hanging up on the wall. That plate can be unscrewed and removed, and it's circuit board material. So in here we have a circuit board. We have multiple little features. We've got our lithium battery which backs up the time when the power is off. We have a DC socket in which can take power from a USB connection, and we have a DC socket in that can take power from 9 to 12 volt supply. Some other items in here, we've got a microprocessor. It's an Atmel AVR microprocessor. There's a little real-time clock device with a crystal that it uses to get the information from, and that is fed into the microprocessor via a 2-wire I2C serial data transfer. We've got some diodes, some surface mount resistors, and you can see where there's a lot of LEDs that have been soldered on the back. Returning to the front, as you can see, the LEDs are arranged in groups of 3. There's a single LED in the center which represents a dot, and when the outer 2 LEDs are lit up, it represents a dash. Because every character will have at least a dot, the center LEDs are always hardwired. At the very bottom we have a small photocell, and that's hooked up to the microprocessor as well so that it can detect when it's dark. And that will then use pulse width modulation to dim the display for nighttime use. If we want to, we can put a tinted acrylic panel on the front of the clock, and that gives a little bit more contrast during the day. We'll just remove that panel for the moment. I want to show here that the entire clock is made from circuit board material with a black solder mask. That gives it higher contrast. Here are the panels that make it up. We have the rear with holes in it for where the time adjustment is made. We have the main circuit board, which has got a component legend on the rear, and just the points for soldering on the front where the LEDs go. The sides of the clock are made up of these strips, which are assembled into a square, then soldered together. There's 4 of those. The bottom section's got a notch cut out of it, which corresponds to a notch that's been cut out of the cover down here. That's so that when the cable leaves the clock, it can come from underneath or it can come out the rear. There are 4 brass threads, 1 in each corner, which allows the rear cover to be screwed on. Right, so let's have a look at some more of the ingredients. These LEDs are green when they're illuminated, otherwise clear. The fronts are a little bit too transparent, and to make a higher contrast, I did lightly sand the ends of these LEDs when the clock was finished to try and diffuse the light that was coming out a little bit more. That was quite successful. So there's quite a pile of those LEDs. Move that to one side. We have a string of surface mount resistors. We have our lithium battery, some low voltage drop diodes. Okay, this device is the microprocessor. It's an AVR Atmel AT-Mega 32A. It's been programmed in assembly language over several thousand lines of code. We've got various other surface mount devices, a voltage regulator, a MOSFET, and some push-button switches. One of the things we discovered when we assembled this clock is that a little bit of light comes out the sides of these LEDs, which is unfortunate when you're looking at the clock from an angle. And we have a fix for that. After the clock is assembled, we put a little loop of heat shrink around each group of 3 LEDs. That means from the side, there's no light coming out. That also helps to improve the contrast of the clock when it's finished. Okay, that'll do. Let's get into it. We've shifted operations to the workshop. Before we get going on assembling this board, I'm going to tell a couple of things. One is about the solder we're going to use. This is extremely fine solder. It's 0.35 millimeters thick, and I'd recommend it for any time you're working with surface mount. Having a fine iron is important. Having very fine solder for surface mount work is very important. So get some of that before you start. We're going to do all of the surface mount parts first because we need that space for moving around. The best way to do that is to figure out where the part is going to be. In this particular case, I'm going to do the little clock chip first. Find one pad and put a little bit of solder on it. Okay, so only the one pad has got solder. Now I'm going to try and pick up this chip. I've got some special tweezers here. These are called reverse tweezers, so they grip the device even though you're not holding it tightly. And we've got our first device. Each device has got a dot on it or a chamfer on it. We have to make sure we get this part in on the correct orientation so that pin 1, as designated by the little square next to the chip, lines up with either a dot on the chip or a beveled edge on the side of the chip. I'm going to solder just the one pin. Now I remove the tweezers and have a closer look. Make sure it's centered. It's a little bit hard. Maybe I'm going to move this one over a touch. If the chip is not exactly centered, you will have problems. That looks pretty good to me. With the chip centered and soldered on one pin, I'm going to solder the diagonal pin. With the diagonal pin soldered, it shouldn't move anymore, but I need also to make sure that it's definitely flat to the board. If it's raised slightly above the board, then you're going to have some problems soldering the rest of the pins. So I'll put a little bit of weight on the chip and just reheat that first pad. Now we just solder the rest of the pins one at a time. The next small chip is a little logic chip, an AND gate, and that's this 4081. There should be a place for it here on the board someplace. There it is there. Same deal as before. We'll put a little bit of solder down. Work out the orientation. In this particular case, pin 1 is signified by a line across the front of the chip. That it also has a bit of a bevel on there if you look more closely, but there is a line across the front of the chip, therefore that is pin 1, and that will correspond with a white square here. As I solder each pin, I pull the iron sideways away from the pin. That just draws out the flux, but you can't afford to wait too long because you can overheat that pin. If by chance you join two pins together, that's okay, it's not the end of the world. We use a different technique to remove the extra solder. We have this substance called solder wick, which is essentially just copper braid with a bit of resin in there. And you can use a little bit of that to mop up the solder between two pins that have shorted out. That's the second chip done. Now for the microprocessor. This microprocessor is the finest of the lot. I'll just pick it up and bring it in camera. There's a whole bunch of pins, 34 of them I think, and they've all got to be in the right place. It has a dot in one corner of the chip here, and this has to line up with the white square on the footprint. So I've got to turn it around 180. Because these ones are closer together, we have to be very careful to get it right. All right, that's the orientation. We'll put a little bit of solder in one corner. Once again, we don't want to spend too long here because we don't want to overheat the pads. A little bit of solder there. I'm going to try and position this chip. I've got to get it just right on two axes or it won't line up. Take time to have a bit of a look under a magnifying glass. That might help to show what the chip looks like. Sometimes there's a build-up of resin around the chip and it's a little bit hard to see if it's making a good connection or not. So what we can do is spray it with a little bit of alcohol. And just work around the chip a little bit. That removes the excess flux from around the chip and lets us have a closer look to make sure that all connections are through to where they should be. Next we'll mount two semiconductor devices. These are in a D-pack style, which look identical but they are very different devices. This one is a MOSFET used for switching the LEDs on at high speed so we can dim them. This one is a voltage regulator which takes our 9 to 12 volt input and gives us a 5 volt output. While they're both the same shape, don't mix them up. So here's the voltage regulator. We're going to plonk it over here onto the voltage regulator footprint. Same deal as before. A bit of solder on one pad for positioning. That appears to be centered. A bit more solder on another pad. And we have to heat up the tab at the rear and make sure that the solder soaks around it and grounds the entire device. The next step will be soldering in the surface mount resistors, and there's quite a lot of them. They're dotted all over the board. They're all 1.2K resistors and they come on a paper tape. That's what we've got here. This is the resistor paper tape and we're going to have to work with it. It's done on paper tape so it can be loaded by machine in places that are doing lots of boards in one go. Just to be careful, we're going to unload the paper tape onto a little tray, in this case a lid off a takeaway food tub, and the parts should just all fall out. Make sure there's no resistors left in the carrier. That's all good. We can throw that bit of paper away. We can throw this piece of plastic away. And we now have a bunch of resistors. Some are right side up, some are not. But we've got to approach these in the same way. That is, we put a little bit of solder on one end of the pad and then solder the part into place. This is where the reverse tweezers come into their own, so we don't lose the parts. Now, it should be pointed out that all of the resistors, all of the surface mount resistors on the board are all 1.2K, except for this one next to the MOSFET. That one's stored separately and it's a 220R or 220 ohms. So that one's stored separately and shouldn't be mixed up with the rest of these. Okay, after that little fast forward, we have soldered in place all of the surface mount resistors except for this very last 220 ohm resistor. If you're working from a kit, you're going to need a few extra spares because one false move and these resistors will only ever be found again by the vacuum cleaner. They're very small. I'm just going to elevate the circuit board a little bit onto some wooden blocks to make it a bit easier to get the through hole parts into the board. Because it's a through hole plated circuit board, we can actually solder them from the top. We don't have to flip them over and solder these parts from the back if we don't want to. It's often easier to do it this way. We have these little push button switches. They only fit into the board one way, and there's 3 of them. We have a capacitor to put in. This is a 470 microfarad capacitor, but it would sit up a bit too high, so we're going to lay it flat. Notice that the capacitor's got one leg longer than the other. Whenever you see a part with one leg longer than the other, it's a sure sign that it's a polarized part and that the long leg has to be oriented towards the positive side. So down here where the capacitor is going to go, we can see that there's a positive and a negative, and we're going to put that capacitor in with the long leg to the positive, and we're going to roll it over. Like that. We have a DC coaxial socket. This is if we're using a 9-volt charging source. That can only fit in one way. That one will have to be soldered mostly from the other side, but we can get around the edges and put a little bit of solder on. I'm going to use some slightly fatter solder here, just so it doesn't fall out when we flip it over. What else have we got? We have the battery. We do have to be a little bit careful with this battery, because once the battery is in, the circuit board is effectively live and is going to be drawing some current. So let's just turn that around a bit, get the orientation right. It fits into one place. This part here between the tweezers is the crystal for the clock. It has 2 legs. If I separate them slightly, we should see that. It doesn't matter which way it goes into the circuit board, but it does have to go in. Next to the clock chip, there's a spot marked XTAL. It's going to drop into there, and it can lay flat. That establishes the time base for the clock chip, and it keeps pretty good time. It should be just a few seconds per month, and that's effective even if the power is turned off. And now we have some diodes. These little signal diodes look like 1 in 4148 signal diodes, a very common garden variety signal diode, but they're not. These are called a BAT85. The BAT85 has a lower forward voltage drop than a regular diode, only about 0.1 of a volt. There's a place here for 8 of them to go in, so let's place those in. Still make sure that they're oriented the right way, with the black stripe on the component lining up with the white stripe on the circuit board. Those 8 diodes are in place. Now we can solder them. Have to be careful not to heat up the buttons, because they're a bit close, and it's very easy to lean the soldering iron barrel onto the buttons and melt the tops of the buttons. But we won't be doing that today. With the diode soldered in, we can remove the pigtails from the other side. This other side will eventually be the front of the circuit board. An important part to mount is this little 6-pin header. It's 2 rows of 3 pins that must solder into the circuit board, but this one must be soldered from the other side. So we're going to pop it in place, but it's still loose. We don't want it leaning over, so that's a bit of a problem. What I usually do is flip the board and hold it with one finger, but not the pin that I'm going to solder. Then I solder just one pin. Just quickly, so I'm not burning my finger. With one pin soldered, I'll flip it over and have another look and see if it is square. It's slightly out, so I can reheat it. There we go. As long as only one pin's soldered, we can reposition it until it's sitting quite square. But if we've soldered all 6 pins and it's leaning, then it's much harder to straighten up. There are 2 more parts to solder onto the circuit board. One is this little photocell, or LDR, light dependent resistor. This has got a mount on the front side of the circuit board facing forwards, so it detects daylight, and when it gets dark enough it will tell the little MOSFET to dim all of the LEDs in one go, so that the lights aren't too bright at night. So we'll pop that one on the other side in a moment. One of the other parts that we've got to mount yet is this little mini USB socket. It's a horizontal socket, and this provides power to the clock if we're powering it from a USB connector or a USB plug pack. One word of warning: when these mini USB sockets go into a circuit board, they sit very flat. And if the connector is a little bit bulky, like some of the supermarket extension cords, it will have problems getting into the socket because it will hit the circuit board. So as you put this connector into the circuit board, just lay a screwdriver down at the front before we snap it into place. And we're going to mount it at a slight inclined angle going up, and that makes sure that the connector has a better chance of going in. The pin connections for it, the electrical connections, are on the other side. We'll do that in a moment, but while it's in the correct position, we'll solder the case of the connector like this, and do it at 4 points. This gives it a bit of mechanical strength. So that power connector is in place. We're going to flip it over, do the electrical connections for that socket, and then we're going to mount our light dependent resistor down the bottom here. So let's turn him over. First of all, the LDR, it's got two fairly long wires. Polarity is not a problem, the leads are the same length, it can go in either way. Just sitting a little bit proud, like that. And I should be able to tuck some solder underneath without too much trouble. There we go, the LDR is in place, and we've got to do the connections for the power connector, which are here. They're very fine. Once again, take your time. Now, something I want to point out, on the back of the board here, every LED position has got a tiny little minus and a plus, minus and a plus. And the plus has been deliberately oriented towards the top of the circuit board. So when we flip this circuit board over, we must note that every single LED that goes in, which has one leg longer than the other, the long leg is going to go towards the top of the circuit board. Otherwise, we'll be putting it in the wrong way and it won't work. With the circuit board slightly elevated, we can now push the LEDs in. There's a lot of them to go in, so we'll do a bit of a fast forward here. So what I've done here, I've got just one row of LEDs that it's been inserted into the front of the circuit board. I've been careful to orient it so that in each case the long lead is towards the top of the board. That gives it the correct polarity, and I've straightened it up while only one leg has been soldered. So they're all in a row now, and now I can solder the second leg of each LED without moving them around, with the knowledge that they're going to be quite straight when it's done. So let's solder the second leg of that row. This is where it's good to be a little bit quick, because the LEDs don't like excessive heat on them. And while we might have an LED securely soldered into place, when it comes to operating the clock for the first time, we might find one or two LEDs will not work, or they work but they flicker of their own accord. That will be because the LED was overheated during soldering. There's a provision here for a 2-pin header. This is where a little jumper can go, where it selects either 12-hour operation or 24-hour operation of the clock. It's fairly rare for 24-hour operation to be selected normally, but if the clock is being used in the shack for overseas work, then sometimes it's useful to have a clock set to GMT in 24-hour time. So we've made provision that this clock can work in 12 or 24-hour time. I'm going to pause the video here while I insert the other rows of LEDs. Okay, through the magic of video, we've fast forwarded a little while and we've got all of the LEDs soldered in place at the moment. The entire construction project should take about 2.5 hours if it's been done at a normal rate, but this may well be spread over a few sessions for convenience. I'm just going to turn the board over now. The microprocessor should come pre-programmed with the correct software in it if it was set up in kit form. But if it wasn't pre-programmed or a program needed to be changed, then we would use that 6-pin header. This is a serial programmer which connects to a PC and transfers the program into the clock. We would normally be making this connection here, plugging this little device into a PC and transferring the program into the chip. Then it would wake up. We're going to test the clock now and see how well it worked. I'm going to provide power via the USB connection because it's the easiest way to do it. Okay, so we have a power connection going in. I'll flip this board over. It should have a startup sequence where it operates every LED column in a row, one at a time until they've all lit up, and then it should start to show the time. At the other end of this cable, I've got a little battery bank with a USB connection. So I'll just plug this in. Okay, it looks like we have our clock. This one's counting in seconds. 4, 5, 6, 7, 8, 9, 0, and it steps on to the next, so that's all looking good. So this is our seconds, this is our minutes, and this is our hours. If I push the time set button, which is over in the corner, I don't know if we can see that, if I flick that one, we should get one of the ranges flickering. Right, that's the hours. And we can then advance those hours until we get the time that we want. Once we have the hours set, we push the set button once more and we have the middle rows flashing. Note that because the center LEDs are hardwired, we're only flashing the outside LEDs, which makes things difficult if it happens to be sitting at, say, 55 minutes in the hour, because none of the LEDs would be enabled. But that's okay, that gives us enough to work. And we can press the advance and set the number of minutes until we get the correct time. After we've set the minutes, we press the set button one more time and it goes back to regular clock mode. That's all good. One of the issues that we do have with this style of LED is that because it's water clear, the light leaves the LED and doesn't leave much of a footprint. So one of the things that I found useful with this style of LED was to lightly sand the top of the LEDs to make it a little bit more opaque. That makes the dash characters a bit more outstanding. We'll do that shortly. One of the other issues with these LEDs is that there's a bit of light which comes out the side of the LEDs, and that kind of detracts from the dot and dash characters. So to help fix that, the kit should come with a selection of heat shrink sleeves. Now I've got a little bag here. We'll open it up. These are just small pieces of heat shrink. We can place the heat shrink over each group of 3 LEDs. This hasn't been heated up yet, I'll do that in a moment, but when I put it on the edge, you will note that we're not getting the light from the sides of these LEDs anymore. A bit of a wave of hot air and they shrink around each group of 3, and that gives us a higher contrast between the dots and the dashes. That heat shrink is grabbing all of the LEDs quite nicely now. Now all the heat shrink is on and the LEDs have been diffused slightly on the front. We should get a higher contrast. I'll turn this overhead light off and let's see what it does. There's one more thing I do want to test while it's in this position, and that's to see if it automatically darkens when the light conditions in the room darken. So if I cover up the photocell here on the end, it should darken. And it does. So it's reading that analog channel from the photocell correctly, and it's automatically dimming after 1 second of darkness. That's good. Now we can move on to the final step where we put the edges onto the board. With the clock now operational, there's only a few things we have to do to complete the project. One thing we can do is cut the excess pigtails off from the front of the circuit board and get a black felt tip pen and go over some of the larger solder pads. This can take a few minutes and it's not essential, but it does help to improve the contrast between the board and the LED lights around it. So we're going to turn the board over and we're going to apply the edges to it. For this, I'm going to remove the power. We don't need that for the moment. And I'm going to remove these wooden blocks. With the side panels, there are 4 of them, but each one is different. On the display itself, the corners are lettered with A, B, C and D. So that means that one of these panels is going to correspond with it. This one has got a C and a D on it, so it means that it's going to go this way around. It's got the word rear on it, which should be on the same side as where the microprocessor and the battery is. So that one's going to be on this side. We can tack it together, make sure it all fits, then we can put more solder on. This is a 1.25mm solder thickness. So let's just get a little bit of solder in one spot and work it together. This shorter panel marked A and D has to go at the bottom because it's got a notch out the bottom for the power cable. If you're not sure by looking at the front of the clock as to which is the top and which is the bottom, check out where the photocell is, because the photocell should always be at the bottom. As you can see, it's slowly coming together. Bit of solder in this corner. In each corner there's another pad which we haven't touched on yet. There's a small square pad, and that's to receive the threads, the brass threads, which will hold the rear cover on. These are also soldered into place. Once enough solder has gone onto the pad, the post tends to self-center. It floats to the middle of the pad. We had to leave these posts until last, otherwise it would have been too hard to get the solder into the corners. That will only take a moment to cool, and we can test the alignment out of the rear panel by placing it over the 4 studs and hoping to see if the holes line up with the threads that we have. That alignment looks pretty good. Now we can safely solder the rest of the pads and lock that whole circuit board in forever. The rear cover gets to be held on with 4 bright stainless steel screws. It's now ready to introduce to the shack. Well, this concludes our video today. I hope you enjoyed it as a construction project. It's a good exercise in how to work with surface mount components, and that's always going to be in good stead for any kind of construction projects in the future. But you also finish up with a very good, very stable clock. and something that's a little bit different. Bye for now, and let me know what you think in the comments below.